morning, everybody. Thank you very much for coming to Mobileye's very first CES presentation. Today's presentation contains forward-looking statements that should be understood to be predictions based on our current expectations regarding future events, and many factors described in our SEC filings and releases may cause our actual results to differ from any such predictions. We ask that you refer to the full disclaimer in the filings. Now it is my pleasure to introduce the co-founder, chairman, and chief technology officer of Mobileye, Professor Amnon Shashua.
Good morning, everyone. I'll focus today on, except one slide, everything else is on the future. To focus on the next 5 years, specifically the next 5 years. I'll talk a bit about 5 years later, but the focus is on the next 5 years. I have another goal in this lecture, in this talk, is I've noticed over quite some time there's a lot of confusion about autonomous driving. There are different types of sensors, cameras, radars, laser scanners. There's all sorts of notions of mapping, algorithms, deep networks, not deep networks. And this kind of confusion, at first I thought the confusion is deliberate. It's kind of fog of war. But now I come to believe that people simply don't know. And people copy concepts from each other. Down the road there's someone who does know, but this someone doesn't share what he knows. So the first 10 minutes is trying to put order in what does it mean autonomous driving and what are the different directions of reaching autonomous driving. And that will put context into the remaining of my talk. So let's start. In terms of content, the first part is I'll talk about the ways of achieving autonomous driving, and I'll put together the notion of sensors, mapping, and other functions that are pillars of reaching autonomous driving. Then I'll talk about sensing, 360-degree awareness sensing, what are the algorithms that we launched and what are we about to launch in the near future, and what is our roadmap. I'll talk a bit about driving control, which is a topic that people don't talk about in the case of autonomous driving, and it is a topic that is at least as important as sensing, and in some cases even more difficult. And then I'll focus on maps, and this will give context and more details about the announcements that were done yesterday by General Motors, by Volkswagen, the keynote, and our press release that we released this morning. So in terms of the present, I'll just 2015 in review. The beginning of the year, when I gave a talk at the Deutsche Bank Auto Show, I mentioned that we are going to have 9 launches of IQ3, and here we have the 9 launches. 8 of them we can say who the car manufacturer is. The 9th still not yet released. There's a lot of focus on automatic electronic braking, AEB. There's an industry first AEB which went out on the Audi Q7 at the beginning of the year. There's vision only AEB in several car manufacturers here. Some of them are fusion. There's industry first hands-free driving, the Tesla Autopilot, and so forth. In terms of 2016, we have 5 new launches starting from the middle of the year, 50 new car models. So by 2016, we'll have 273 car models. When we went for IPO a year and a half ago, we predicted 240 car models. So we're better than the prediction. And there are going to be new functions coming out, more semi-autonomous driving like the GM Super Cruise, more free space detection functions to detect any boundary for semi-autonomous, full speed ACC, second generation ACC, which is camera only, coming out. That will be an industry first. Animal detection by Volvo, which is an industry first. Okay, so that was for the present. Let's now go into the future. So I'm going to talk about the ways, and there are 2 ways, 2 main camps of reaching full autonomous driving. So full autonomous driving is level 5 autonomous driving. The driver is completely out of the loop. The driver doesn't need even to be behind the steering wheel. So how do we reach that stage from a technological point of view? So I'll start with, there are 3 pillars of autonomous driving. I'll list the pillars not according to their importance, but according to their clarity. So starting with the most obvious and clear concept, and then moving on to concepts that are less and less clear. Okay, so the first concept that is clear is sensing. You need to have sensors around the car. Those sensors have a 360-degree awareness, and they build an environmental model. Environmental model, you know where all the moving objects are, where all the drivable paths are, where all the path delimiters are, like curbs, barriers, guardrails. Each path, you know where it leads to. This is the highway exit. This goes straight. This goes right. This goes left. So it's an environmental model, and this is what you get out of sensing. So this is more or less clear. The second pillar is mapping. Now, mapping is less clear because the assumption that you need maps is also questionable, because we humans, we don't need maps to drive, right? We can go to a new place, rent a car, drive, and we can drive safely. Of course, when we drive in a place that we have driven many, many times before, we feel more comfortable in driving, but still, we can drive in a new place. So there is a proof of concept that you don't need maps. But there is a reason why you do want to have maps, and I'll get into it. But in the area of maps, things are not clear. You have navigation maps, you have what is called high-definition maps. TomTom and Here have different definitions of high-definition maps. Then you have the Google 360-degree, 3D, very detailed centimeter scale maps. So what exactly is meant by maps? Third one is planning. Planning is a topic I haven't seen anybody talk about it. So what is planning? What is driving policy? Driving policy is the answer to the question why a 16-year-old kid needs to take driving lessons. Think about it for a moment, right? We don't take driving lessons in order to train our sensing. We know how vehicles look like, pedestrian looks like. No, so it's not that. We don't take driving lessons in order to learn how to control a car. Today, with the automatic gear controlling a car, after 10 minutes, you know how to control a car. We're taking driving lessons in order to learn how to merge into traffic. It's a multi-agent game. There are behaviors that you need to learn. You have other drivers on the road. Some of them follow the rules. Some of them bend the rules. Some of them violate the rules. Some of them are aggressive. Some of them are courteous. You need to learn this. There's all sorts of behaviors that you need to learn. And we know it is difficult because it takes us dozens of lessons until we get our driver license. Then we're mediocre drivers. It takes us years until we become good drivers, and some of us never become good drivers, right? So if it is difficult for humans, why should it be easy for computers? Right? So reaching autonomous driving, it's not only how do I get an environmental model by my sensing, whether I have maps or don't have maps, how do I take this information and decide where to move and how to move? Okay, so this is a topic that there are technologies, and I'll talk about it. So let's start about understanding how to put together maps and sensing, and what we'll see that there are two main camps, and you need to know which camp you are on, because once you are on a camp, you are committed. You cannot cherry pick ideas from the other camp. Right? So once you're in a camp, you're there, and you need to know that. And what I notice is sometimes people who talk about autonomous driving do not know which camp they are on. Okay? So in terms of sensing, things are relatively clear. You have cameras, radars, and laser scanners. Cameras have the highest density of information. We're talking about hundreds, tens of millions of samples per second, right? You have a megapixel image, 36 frames per second. So you have at least 36 million samples per second. By 2020, we have cameras of about 7 megapixels, so we're talking about hundreds of millions of samples per second. LiDARs have hundreds of thousands of samples per second. Radars have thousands of samples per second. Radars are more robust in terms of weather conditions. They can see through areas that cameras cannot see, and even laser scanners cannot see. Laser scanners and cameras they're optical based, so they have more or less the same weaknesses. With cameras, there's a big challenge of image variability. The image looks different at day and night, at dusk, low sun, rain, weather conditions. So the algorithmic challenge of processing camera information is very, very high. And then you can have all sorts of claims of what sensor can do and what sensor cannot. For example, laser scanners cannot sense texture in a reliable way. They can sense a three-dimensional structure. But it's more or less clear. Professionals in the field know what each sensor can provide. With mapping, it becomes a bit more messy. So from no maps, and we humans are proof that there's no need for maps in order to drive, to navigation maps, the kind of maps that we are all aware of. Then there's the high definition maps, which one needs to define it, and there's more than one definition of what high definition maps, but you can imagine this is higher resolution maps, whatever higher resolution means. Okay? And then there's the Google's 3D centimeter scale map. It's a cloud of point, 360-degree, moving forward. We're talking about 1 or 2 gigabytes of data per kilometer, something of that scale. But when you talk about mapping, there's another dimension to it, and that's localization. So when you don't have map, you don't need to localize yourself. That's fine. If you have navigation maps, you need to localize yourself at an accuracy of about 10 meters, and this is the GPS. The GPS provides you this localization, no problem. The other maps, the high definition maps, and this Google 3D maps, they require localization, and very accurate localization. We're talking about 10 centimeter accuracy of localization. So you need to think about how do you provide accurate localization, right? It's an issue. Okay? So when you talk about maps, you have to think about also localization. Just having a very, very detailed map without being able to localize yourself in the map doesn't help you. So these two have to come together. So let's look about the two different camps. And I call these camps the somewhere and everywhere camps. The somewhere camp is the following idea. We start with autonomous cars somewhere. Think about Mountain View. Think about a gated community somewhere. You take that someplace, you map it until that there's white smoke coming out of it, and you have full capability there. So somewhere with full capability. The other camp is everywhere with partial capability. So you want to have your capability to be activated everywhere on the globe, because when we buy a car, the car is activated everywhere. So everywhere, but you start with partial capability, like semi-autonomous driving. You don't have full capability. So the camp on the left is led by Google, Baidu, but Google is really the leader of this camp. And the camp on the right is mostly the car industry. Now, the ultimate goal and how it is being done is with the camp on the left, you have a 3D detailed map. As I said, it's centimeter scale map. It's gigabytes of data per kilometer. And you can use a low resolution sensing, like a laser scanner. You can use a sensor that doesn't record texture, just the shape, and doesn't have to be very, very dense, because the map itself, once you have recorded it, you can use the principle of subtraction. So you take your sensing, you find a match in your map, and then you subtract all the stationary objects, because the map contains only the stationary objects, and you are left with only the moving objects. So even if you have a small number of sampling points on a moving object, you can still pick it up. So you can use a laser scanner as your primary sensor only if you have a detailed map. So this is why Google can manage only with a laser scanner, and others, they need additional sensors because they have the very, very detailed map. In the car industry, we're talking about a low-resolution map, the navigation maps. This is what exists today. And high-resolution sensing, these are the cameras. And you have also radars for redundancy, fusion between camera and radar. Now, the ultimate goal is everywhere with full capability, right? This is what both camps want to reach. So now let's look at the challenge of each camp. The camp on the left, their challenge is scalability of geography, going from somewhere to everywhere. Now, scalability of geography is not only create the map, not only in Mountain View, but go and create the map all over the United States, all over the globe, but also you have to address the problem of updating the map. Now, this map is safety critical because you're going to do autonomous driving using the data from the map. So the map has to be continuously updated. So it's even near real-time update. So how do you do that? I don't know. This is the challenge that the camp on the left has. Scaling up from somewhere to everywhere. What is the challenge on the camp of the right? They also have challenges. I'm not saying it's easy. Nothing here is easy. The challenge on the camp of the right is stronger artificial intelligence, going from partial capability to full capability, you need more artificial intelligence. You want to reach human-level perception, human-level cognition, because humans can drive. So this is the ultimate goal. You want to reach that level of artificial intelligence. This is called strong AI in the AI community. But reaching strong AI, it's risky. We don't know how much time it will take. It could take 5 years, it could take 50 years. Right? We are all hopeful it will take a few years, but there's no guarantee. So what that camp says, before we reach strong AI, let's settle for stronger AI and compensate for the lack of having full AI capability is to have a very detailed map. So the detailed map allows you to see beyond sensing. Because if I know where I am and my map tells me where are all the drivable paths, they tell me which path goes where, then even if my ability to interpret sensing is limited, this type of information can go as a layer on top and compensate for my limited AI capabilities. Okay? So this is why there's this push into high-resolution maps. So the challenge, the camp on the right is stronger AI, better algorithms, more improved algorithms. This is why people talk about deep learning and all of that, and higher resolution maps. And this is where I want to focus my talk. This is where Mobileye is playing, right? Stronger AI and maps, and how do we do that? Okay, so it's understood the context of my talk, I hope. So what is our approach? So this is the goal, higher resolution maps and stronger AI. So our idea is a very, very simple idea. We replace the and by the by. So we use our capability to build an environmental model, capability of doing artificial intelligence, interpreting sensing data to make the map creation, the high-resolution maps, become a much simpler problem. Rather than treating it as two different problems, one company building a map, another company providing sensing interpretation, we have one unit that leverages the ability to interpret a scene in order to create maps that are much more clever in their size, the ability to update them, and the ability to use crowdsourcing. This was the basis for the two press releases or the two events that happened yesterday at Volkswagen and GM. Okay? So how do we do that? So what I'm going to talk about in terms of stronger AI is to talk about 360-degree sensing. How do we build environmental models? What are the tools? And this issue of planning, the driver policy. This is why people take driving lessons. So all of this is under stronger AI. In terms of the higher resolution maps, we have here a novel idea which goes as follows. Rather than having a detailed 3D description of the world, we're looking at a sparse 3D. We're looking for landmarks like signs, poles. I'll show you. There's a list of different landmarks that exist in the scene that we can pick them up using AI. And the density of information to have it only 1D. So we need the lanes to be dense in terms of the amount of information we're picking up from the lanes, but we don't need density, full density in 3D. So it's sparse 3D, dense 1D. This idea, if you put them together, comes up to about 10 kilobytes per kilometer. So 10 kilobytes per kilometer is about 5 orders of magnitude compared to gigabytes per kilometer. Okay? And this would be crucial because this amount of data is nothing, and this amount of data can be then transmitted using crowdsourcing from all cars on the road to the cloud, and then the cloud maps are being built and then sent back to vehicles. And it's crucial that it will be a very, very low bandwidth. It has to be a very, very small amount of data to make this work, right? You cannot send raw data. You cannot send images, videos to the cloud. It will not work. You have millions of cars sending data. The infrastructure we have today will simply not hold this. It has to be a very, very small amount of data. And this is what we did, and we call this road experience management. Okay? So this is now what I'm going to talk about. I'm going to talk about on the left, about the stronger AI. What are we doing in stronger AI? And then I'm going to talk about what I have here on the right. How are we building these maps? What's the definition of the map? I have to put quotation marks around map because it's not the kind of map that you are used to grasp. It's not a navigation map. It's something else. It's a different beast. But it's something that allows a car with stronger AI to drive fully autonomous. Okay, that provides the missing piece. How do you go from where the car industry is today, which is partial autonomy, high resolution sensing, which is low cost, to fully autonomous driving? So sensing in 360 degrees. So monofacing cameras. This is the heavy heavy in terms of heavy lifting in terms of driving assist today. It's a powerhouse of all the processing that's going on. Collision avoidance. Today it has a 50-degree field of view. In 2018 it will be 75-degree field of view because of regulation coming from Europe that requires wider field of view. 2019 it will be around 100 field of view. Today the imagers are 1.3 megapixel imagers. In 2019 there'll be 1.7 megapixel imagers. In 2020 we have a novel concept that we shared with 2 camera manufacturers, with onsemi and with Sony, to build 7 megapixel sensors. These are different from consumer cameras. I don't have time to talk about this. With automotive cameras, you need very, very low light sensitivity. Consumer cameras, you don't need that. So if you want to build a 7 megapixel sensor for automotive, you have to be clever. So we have a design and it's going to be built, and from 2020, we predict there'll be 7 megapixel sensors. Okay? Then there is the trifocal, where you have 3 different fields of view. The purpose here is to enable highway automation. So highway autopilot, a safe highway autopilot in which you can really disconnect from the driving experience. You still need to be behind the steering wheel, but you can really disconnect from the driving experience. There are 4 production launches, 2017, 2018. Typically, it comes with 4 corner radars, a front and back front radar, and in some cases, a laser scanner. Mostly, it's the Valeo Scala laser scanner. Then, in order to support fully autonomous driving, we're talking what we call full vision. This is the trifocal plus 5 cameras around the car. These are not the parking cameras. The parking cameras, they see only very, very short range. You need to see far away. So the cameras are placed differently from the surround parking cameras, provide a 360-degree field of view. It's mostly supported by our IQ4, but one of the programs will come out with 3 IQ3s to support it. It will start somewhere 2017. It will start with partial functionality, but the hardware will enable full functionality by simply improving the software over time. So in a period of 2-3 years, in terms of technology, we'll be able to support fully autonomous driving from the point of view of sensing. I'll skip all of this. So let's talk a bit about sensing, learning to sense. So learning to sense falls under the machine learning category, what's called supervised learning. Supervised learning, there is a clear input-output relationship. You have an image, which is the input, and output. You can ask yourself, what is in a bounding box? Tell me, is it a car, is it a pedestrian, is it a traffic sign, what is it, what kind of traffic sign, and so forth. Or detect a free-form pattern, like tell me where the free space is, where can I drive? Or tell me where the path delimiters are. This is a curb, this is a barrier, this is a guardrail. All of this are very clear input-output relationships that you can learn. You can learn using lots and lots of data that is labeled by people. And deep learning is a modern tool for doing that. I'll not get too deep into this because many people are talking about it, and I guess you're all tired of listening to deep learning talks. But this is the modern technique of today using machine learning, where the input-output relationship is quite clear. Now, what is special about deep networks at Mobileye? First, we started 2012, and we already have serious production. The Tesla Autopilot contains our deep learning functions, like the free space, holistic path planning. There are certain scene recognition elements going on there, which are using deep learning techniques. Our deep learning algorithms encompass a very wide span of customer functions. It's not only object detection, an environmental model, it's path planning, scene recognition. There are many, many modules. Each one of them is trained end-to-end with a deep learning module. And the kind of problems that we solve have unique challenges. This is not the kind of the run-of-the-mill type of problems that you see coming from academic papers. First of all, we have real-time constraints. We're talking about high-resolution images working at 36 frames per second. The input-output modeling is sometimes very, very challenging, and I'll show you some examples. The network architecture that we need to build requires thought and ingenuity. The utility function, the cost functions require a lot of ingenuity. And there's a lot of innovation going on these networks. This is not kind of a garden variety network that we take from someplace, we copy from some academic paper, and we simply run it with lots of data. This requires a lot of effort. And object detection is kind of the least interesting function that we work on. There's much more interesting functions. And I think I write here most likely, because maybe I'm making a mistake here, but I think that we launched the industry first embedded deep network, not only in automotive, but in any industry. So Google has deep networks, algorithms like Google Translate. Facebook, I imagine, have all sorts of deep networks running. They have a very strong team, and they have lots of deep networks running in their services, but none of this is embedded. None of this is portable. Right? What we do is embedded, it's portable, not connected to the cloud. We're not sending images to the cloud, and on the cloud we're doing our computations. So I believe that we launched the first deep network product anywhere in any industry. But maybe I'm mistaken. This is why I wrote most likely. Okay. So let me show you some examples. So the first example is what we call 3D VD. So vehicle detection, going forward in vehicle detection, we have to look at vehicles not as an object where you put a bounding box on it, but an object where you put a 3D bounding box, where each face has a label. You know, this is the left-hand side of the car, the right-hand side of the car, the rear of the car, the front of the car. Now, why am I showing this? First of all, the utility of this is because when we go forward in object detection, we need to define vehicles from any angle, kind of cross-traffic kind of situations. Also, when we're putting many cameras around the car, not only cameras that are forward-facing, a camera at an angle sees vehicles at an angle itself. So we need, in order to generalize our ability to work from any camera angle, we need to generalize our definition of what a vehicle is. Up to today, the definition of a vehicle is only a bounding box around the rear end, and here we have to generalize this to a full 3D box. Now, why is this difficult? It is difficult because the input-output relationship here is tricky, because the 3D box is not always visible. Sometimes you see only the rear end, sometimes you see only the side, sometimes you see both the side and the rear, sometimes it's the front and the side. So the input-output relationship requires thought. How do you present it in a network architecture? What is the cost function? And this is something that hasn't been dealt with in any academic paper, hasn't been dealt with anywhere in a forum that publishes papers. This is targeting IQ4 platform, so late 2017, early 2018. And there is one production which is coming sooner, which is running on 3 IQ3s, which will be using this technology. And just as a rule, all what I'm saying, I never talk about something that doesn't have a customer. We don't talk about developments into the future that are not backed by a production agreement. We do many things that are not yet backed by production agreements, and I'm not talking about them. So whatever I show is backed by a production agreement. Free space. Free space is the idea of you take an image and you want to map it to where can you drive? Where is the roadway? And what I'm showing here, the roadway is colored by green. And let me show you, this is quite interesting. So, for example, here you see that the algorithm, which is a deep network algorithm, understood that this part, the curb, and what's above the curb is not part of the road. But let's go a bit further, and I'll stop it in a place which is really, really impressive. Here, when you look at this, the texture of the sidewalk here, of the pavement, is exactly identical to the texture of the road. So how did the system know that this is not road and this is road? It knows that because it learned the context. There's a lot of context processing going on here, so it's not a local, take an area of an image and decide whether it's a roadway or not a roadway. It's a full image, and this is one of the powers of deep networks, that you can leverage context into it. And here again, the challenge is how to model the output. Is the output a label per pixel? If you do that, maybe you'll have a nice demo to show, but it will not work in practice. It will not work at the accuracy that our feature works on. We launched this on Tesla Autopilot a few months ago, and it's an integral part of any boundary function feature from 2016 and forward. So this is a function that is running 36 frames per second, high resolution, and does things like what you see here. We have extensions of it where at the boundary of the free space, there is a label, whether it's we have 15 different categories, whether it's a vehicle, whether it's the side of a vehicle, whether it's a curb, a barrier, a guardrail, and so forth and so forth. So this is trying to give you the environmental model. And here you see this from multiple cameras. So from multiple cameras, we know where the free space is, the boundaries of the free space. On the boundary of this free space, we have a category label. What is it? Is it a curb? What kind of path delimiter is it? Is it a path delimiter of a moving object, path delimiter of a stationary object? What kind of stationary object it is? Another example of deep network is path planning using holistic cues. So in order to support hands-free driving without a map, just by sensing, you need to know where the path is. Now, in situations where you don't see the lanes, like what you see here, there are no visible lane marks. Yet humans can drive quite easily in this case. And what you see here, that the system has learned and predicts the path correctly, even when there are no lane marks. Again, the question is how to model the output. It's kind of a very, very tricky modeling. How to use multi-frame in this case, what kind of a recurrent neural network you need to build here. All of these things are not kind of a run-of-the-mill garden variety problems that people handle. This was first launched on the Tesla Autopilot, and it's an integral part of our lane detection going forward. So let me show you, not in a PowerPoint. This is, I downloaded this from the web. This is someone driving hands-free on the Tesla Autopilot. Okay, and what I want to show you here, so you see that she's driving hands-free, and the point I want to make here, do you see the lanes? Nothing. There are no lanes. There are shadows, there's low light, there are hardly any lanes. There's a lead vehicle. The system fuses information from lead vehicle, but if there's no lane information, the system deactivates. It will not do hands-free driving just because there's a lead vehicle. And this is the power of this HPP, this holistic path planning feature. And you see this is already in serious production, tens of thousands of vehicles already. Driver policy planning. So this was sensing. Let's go to the next part. So the highlight of the talk is the mapping. So give me another 5 minutes before we get to the highlight of the talk, and then I'll open the podium for questions. So the driver policy. Again, remember, this is what we talked about, the reason why you take driving lessons. How do you plan? How do you plan ahead? And this is a topic that I noticed nobody really talks about. People talk about sensing, people talk about mapping, and the notion is that once you have a full environmental model and you have maps, your problem is solved. And this is far from the truth. And you see, I downloaded from the web one of the articles talking about that, today, autonomous driving fleets are too cautious. There are many accidents because other drivers hit the autonomous vehicle, because the autonomous car is obeying the rule to the letter. And this is not how humans drive. And this is true because driving is a multi-agent game. There are behaviors to be learned. And if we want to have a fully autonomous car driving in the presence of other human-driven cars, the autonomous car needs to learn behaviors of humans. Otherwise, you'll simply get stuck in the traffic, everybody will be upset with you, and somebody will hit you. Right? That's the nature of humans. But the point is that it's a technological problem. It's not an ethical problem. But I'm not talking, let's learn the behavior of a drunk driving person right now. We want to drive safely. We want to reduce accidents by orders of magnitude. But there are human behaviors that we need to learn. So what are the challenges here? When you look about sensing is the present. You are given an image and you are asked what's in the image. Or you're given a video and you're asked, okay, take multi-frames and tell me what is in the video. It's a single agent game. There are moving objects, but you treat them as objects. You don't treat them as behaviors. You detect them. So it's only a present. It's a single agent game looking at the present, and it's perfectly predictable. There are input, outputs. If you have enough data, you learn the mapping from input, output. I'm not saying it's easy, it's difficult. If it was easy, I would not be standing here. It's difficult, but it's perfectly predictable. What are the technology? Deep supervised learning is really the modern tool to use, and there's no point even creating a debate on it. This is the modern tool to use. And you have multiple modules. Each module you do an end-to-end training per module. What's happening with this planning, the driving policy? First, you are planning for the future. It's not the present. Second, it's a multi-agent game. You are not the only agent on the road. There are others on the road, and they have behaviors, and you need to take this into account. Third, you are contemplating about what will happen if kind of scenarios, and it's not perfectly predictable. So this creates a challenge. What are the tools for this? The technology is called reinforcement learning. There are some very nice academic research on predicting, on playing Atari games by Google DeepMind. It's called the Q learning, and within the context of deep networks, it's called deep Q learning. The point is that this Q learning mechanism is not suitable for our game. One of the assumptions is Markovian assumptions, that you can fold all the past into the last state. This is true for the host car. It's not true for the environment, for other agents. And there are many other technical issues that make it really not suitable for our space. Now, because this is not a technical talk, what I did, we put a paper on our website, and anyone who has a technical inclination is welcome to download the paper and read what we're doing there. And what I'll show you an example, just to get a feeling of what's going on. Let's take a simulated example of the host car, which is red here, merging into a roundabout. And the roundabout is busy, right? So if you wait until somebody will let you to squeeze in, that will never happen. The roundabout is busy. Now let's play a game in which, in the roundabout, there are two types of vehicles. There are aggressive cars, let's say drivers from Israel, we imported them, or drivers from Boston. Yeah. So an aggressive behavior is that once the aggressive driver sees you, he accelerates. Doesn't want you to squeeze in, right? I accelerate, so you stay there. I'm going to accelerate. The courteous driver, the second behavior, is a Californian driver, right? He'll slow down, let you squeeze in. Okay? Now the point is that the agent, the red car here, doesn't know all about that. All what he's getting is data. And he's trying to merge. At first he'll make mistakes and hit the other cars, and later, because he wants to maximize the reward function, later he will start implicitly learning these behaviors. So what is happening here, you have, so the blue are the aggressive ones, and you see how he accelerated this blue one, and this is the kind of the output that you want to achieve. And this network that we built on the left is during training, so you'll see that the red agent, makes mistakes, he hits the other cars, and gradually over many iterations reaches the one on the right, which I showed you before, that he correctly predicts he knows how to distinguish between these two types of behavior and squeezes itself into the right place. So what I'm saying is that these human type of behaviors can be learned. The simulation that I'm showing you here is only for the presentation. What we are doing is we're building these technologies on real data, on real driving scenarios. It's a lot of work, and it's a technology. It's not an ethical problem. We can have technology that will learn behaviors of other cars in order to support hands-free driving that could merge into traffic in a normal way and not upset other drivers. Okay, so now highlight of the talk, the last to give you time for questions in the last 5 to 10 minutes. So we are now talking about mapping. So the first question to ask is, what should a map enable? So the map should enable two things. One is localization, and I talked about accuracy of about 10 centimeters. So it's 10 centimeters longitude accuracy, it's about 3 to 5 centimeters lateral accuracy. And assuming that there are no obstacles, because our sensing finds out where the obstacles are, where are the drivable paths? This is what the map should provide me. Tell me all the drivable paths, and locate me in this map in a very high accuracy. What are the map requirements to enable an everywhere autonomous driving? So remember, we are now in the everywhere camp. So we talked about sensing, now we want to talk about mapping. So what are the requirements of this map? So the first requirement, that update should be a continuous process. It should be near real time, because again, we're talking about maps they have a critical safety function, or safety critical function. It has to be updated. It's not like navigation maps. So the process must be crowdsourced. We don't see any way of having a real-time update without crowdsourcing it. Now, if we're talking about crowdsourcing, then the data per vehicle per kilometer should be very, very small. So we managed to bring it into a 10 kilobyte per kilometer. Now, this means that transmitting images and other raw signals is out of the question. You don't have bandwidth for it, especially if you want to continuously send this information. Now, I've seen people talk about machine learning algorithms on the cloud. I don't know where that's coming from, right? Everything should be done locally, right? It's a real-time critical safety engine. So this means that advanced processing must be done on board. Otherwise, you cannot send 10 kilobytes of data. You have to do all the processing on board, extract only meaningful information, and that meaningful information send it out, not send out the raw information. And since we're talking about the auto industry, they don't like to pay even a single cent if they don't need to pay it. So preferably not to introduce any dedicated hardware for the task. Cameras are already used for ADAS, and it's growing, the adoption is growing, so why not use the cameras? So all what we'll need to do is just add software. That would be ideal. Okay, so in terms of what are the existing approaches, so GPS is not an answer. GPS could provide you a 10-meter accuracy. Differential GPS, RTK, could be the answer in open areas, but once you get into city traffic, and this is where all the action is going to be, city traffic, GPS is not going to give you the accuracies of centimeters. There is a field in computer vision called SLAM. You can search it up in Wikipedia. The idea there is that every image you look for interest points, and each interest point you have a descriptor. You track these descriptors, you create a 3D map from the points that you are tracking, and then you can localize yourself. It's around 1 megabyte per meter, 1 gigabyte per kilometer. Again, we're back to these gigabytes of data. That's not good. There is the TomTom Road DNA. I don't know if it exists, but they have it on their website. The reason I'm showing it because they talk about 25 kilobyte per kilometer so that people don't get confused. This is only for localization. It uses a laser scanner, so it's a dedicated hardware. It's not crowdsourced, and it doesn't create a map. It's an engine used for localization. So what is our idea? The idea is sparse 3D, dense 1D, and crowdsourced. So the idea is that we look in the image, we look for landmarks. And what we have on the image on the right is an example of landmarks. So these would be traffic signs. There are about 1,000 different tags. Directional signs, there's about 10,000 different tags for directional signs. General rectangular signs, we create an image signature. Lampposts and reflectors. What we calculated is that the worst case you're driving on a boring highway somewhere in Texas. In the worst case, it's once every about 100 meters you find a landmark. Okay? So in city traffic, it's of course denser. So once every 100 meters, you can find a landmark, and you use this landmark to fix your positioning. Here's another example of landmarks from city traffic. Okay? So it's not a per image process, it's a per landmark process. Once you find a landmark, you recognize it, and you need this artificial intelligence, part of the environmental model, to find all of that. Then we create a road model. We take the lanes, the short distance lanes that you see here, and we stitch them together using ego motion. Ego motion is a technique from computer vision to stitch together by calculating the motion of the agent, the three-dimensional motion of the agent, and we create polynomials, 3D polynomials of the left and right lane. And we also collect information about which lane it is in a multi-lane setting, also information about the boundaries, the path delimiters. And the point is that this is 1D information. It's dense, but 1D, therefore the bandwidth of it is very, very small. So the bandwidth of landmarks is about 2 kilobytes per kilometer. The bandwidth of these dense 1D is about another 2 kilobytes per kilometer. Mm-hmm. So the landmarks are used to, it's a local coordinate system. So there's no global coordinate system in this concept. It's all local coordinate systems, and it fixes a localization drift. Once you get to a landmark, you fix your localization drift. And then you use tail alignment, because then you can use the road that you have seen in the past in order to have a better alignment to the map that you have. And the road model is the record location of the lanes and create these polynomials of the lanes and all the drivable paths. What is the crowdsourcing here? This information is being sent to the cloud, and we call the data that's being built a roadbook. Now, the term roadbook is not our invention. I put here the credit. It's by Volkmar Tanneberger from Volkswagen. So when I presented it to Volkswagen, and I talked about the concept, I said, well, this is exactly what a race driver does. A race driver has a cognitive map of landmarks, like say cones positioned in certain places, and when the race driver reaches a landmark, he takes an action. It could be shift gear, press a brakes, accelerate, and so forth. So there's no global coordinate system, just landmarks, and for each landmark you have an action. And this is exactly what we're doing here. We have landmarks, right? And it's all local coordinate systems, and this is why we use this term a roadbook, rather than using the word map, because it's not really a map in the sense that we know what a map is. So this 10 kilobytes of data are being sent to the cloud. On the cloud, it's being integrated. So every landmark, you see it millions of times by other cars, by you driving over that landmark many, many times, and therefore you improve the accuracy of the landmark. So integration is also improving accuracy. And you can also do change detection and know what to update and not update. And you increase, and you build a global map, all using local coordinate systems. Here's an example. One moment, you can go back. So you see here, the point here is localizing the vehicle in this map that was built by the technique that I've showed you, now, and these are all the landmarks that are being sensed while we are driving. Okay, so what are the services? What is this roadbook services? So the plan is to have this for autonomous driving. It acts like a prior, resolving ambiguity in sensing. So if you know where you are and you know where the driver will pass, it's kind of a redundancy over sensing. If you are compromised with your sensing, you can give a higher weight to the map. It gives you an increased foresight. You know where the path, how the path looks like, even beyond sensing. Sensing will give you a 100-meter foresight, and a map will give you infinity foresight. Greater safety due to increased redundancy. You have now a redundancy between a map and sensing, right? So autonomous driving is all about safety. If it's not safe, you cannot reach autonomous driving. So you need redundancy. You have redundancy with moving objects. You have more than one sensor seeing a moving object, and you want to have more than one sensor predicting drivable paths. So you have the sensing predicting drivable path, and you have the map predicting a drivable path. So you get redundancy. And then guidance for complex drivable paths like four-way junctions. Sensing is quite limited in those areas. But there are other map services. I just gave here a number of ideas, and we're working with our OEM partners to think about other map services even before the age of autonomous driving. Now the REM deployment, first deployment is going to be with General Motors, and it's targeting 2016. So 2016 is, in the automotive time frame, it's yesterday, right? It's very, very soon. So we're targeting 2015, and the good news here is that we have many launches with GM, starting from middle 2016, going up to 2019. Every few months we have a launch. And the idea is to piggyback on one of the existing launches. We don't need to create any new serious production program, because all what we're talking about is software modifications to existing programs and using GM's OnStar communication capability, which already exists in cars. Therefore, it can come out quite soon. With the Volkswagen, we signed a memorandum of understanding covering all the agreed principles, mostly commercial principles, and the definitive agreement, the target is to finish this within a few months, and the deployment is planned for 2018. And then we have a third partner, which at the moment I'm not at liberty to mention the name, but it will be revealed soon. And the idea with these three partners is that together they cover about 1/3 of the global car industry. I wrote here 2014, it's about 28 million cars. And not only that, they are positioned everywhere, right? So we want everywhere, right? And we don't want just to work in a certain geographic location, no matter how big it is, we want everywhere. And this gives us the everywhere. And the idea is that 2020, we'll be working with our OEM partners to cooperate with all other car manufacturers. So not leaving anyone out, cooperate with all car manufacturers, and we want to do it in a way that makes sense, and this is still on the sketching board. What is the strategic value of all of this? And I think there are three strategic values. One is from an industry-wide perspective. OEMs can leverage their size. So we're not only talking about technology, we're talking about leveraging size. Because the more cars you produce, the more benefit you have. So it's not only your degree of technological innovation, you have to be a big car manufacturer, right? If you're a small car manufacturer or a non-car manufacturer, no matter how clever you are, you don't have this benefit. So this is the first time where we can really see very, very clearly how car manufacturers can leverage their size and create an asset which otherwise it's impossible to build. Okay? So I think this is the most in terms of strategic value. The second is the camera. The camera is becoming much more than a sensor for driving assist. It's not only a sensor that detects vehicles and pedestrians and does collision avoidance. It becomes part of the brains of the car. It's also responsible for mapping, for creating the mapping, for updating the mapping, for accessing the maps. So now the camera is much more than a sensor. Third is for Mobileye. It's a positive impact on sustaining competitive edge because you need an IQ chip in the car at the end. It opens up the possibility for the central role of IQ3 and mostly IQ4 in the car's ecosystem because now it's more than just sensing. And it's also a new market in terms of revenue. The way we are working with our OEM partners is to find a way in which there is also an increase of ASP, a little increase of ASP on the IQ, but there's also, we are sitting around the table or sitting at the table when we're talking about monetization of these maps later, whether it will be recurring monetization, pay per kilometer monetization, whatever monetization will come out of it is to sit at the table when it comes to monetization. So for us, it's also a growth engine in terms of revenue. It's not only a way to sustain our competitive edge on the IQ chip, we're talking about a new revenue source. So I'll summarize now. There are two camps going forward, and we are on the camp of high definition sensing, which is cameras, low resolution maps, which are the road books, and start everywhere. The other camp is start somewhere. Okay? And the point I'm making here, it's not necessarily a zero-sum game. It's not the success of one camp is the loss of the other camp. I think it's important that both camps succeed, right? We have no intention that the other camp does not succeed, right? Both camps, it's not a zero-sum game. Deep networks and sensing for planning, modularity is key. It means you have to have many modules. Each module you're training end-to-end, but it's not just one big monster algorithm that takes an image as an input and outputs where to drive. That will not work. It will not reach the accuracies that you need. It's modular. Also, the brain is very, very modular, the human brain. Relevant problems require significant ingenuity. There's no such thing as take a pre-trained network or a garden variety network. All of this is all nonsense. It's by people who don't understand what they're talking about. It's off-the-shelf concepts would be good to reaching a demo level. Making demos is easy. Getting a production agreement from a car manufacturer is a completely different ballgame. Driving policy is a challenging problem. This is the planning that I mentioned, and we are fully engaged in that. We're not only engaged in sensing and mapping, we're engaged also in the full capability of going from sensing to action. And the roadbook maps, right? I think I've said everything there's to say about it. So I'll stop here to leave time for questions. I imagine that many people have questions. And thank you for listening.